In the third part of the 2.7 video, we're going to work through this exercise. Find a 3 by 3 matrix that produces the desired two-dimensional transformation using homogeneous coordinates. We want to translate by 3, -5, and it's the translation that requires the use of homogeneous coordinates, and then we want to rotate by 135 degrees counterclockwise around the origin. So we're going to make use of what we learned in the previous video about how a matrix can describe the rotation transformation. So here we're dealing with our 2, and we want to translate by 3, -5. That means we're going to shift 3 units to the right and down -5 units. After that, we're going to rotate about the origin 135 degrees. Because we have two aspects to this transformation, we can deal with them separately, and then we're going to multiply the two matrices that we obtain for each one of those to give us the matrix for the composition of these two transformations. So for the translation portion, we need to introduce homogeneous coordinates because we want to move 0, 0 in R2. We want a point xy1. We're going to think of R2 as sitting in three-dimensional space as the z = 1 plane. So we want the point xy1 to move to x + 3, y - 5, and z stays at 1. And we've talked about already how we can write down the matrix for that. Let me maybe write it in this way. We want a 3 by 3 matrix that will transform xy1 to x + 3, y - 5, 1. And to do that, we want to take 1 times x, 0 times y, plus 3 times 1. 103 will give us the x + 3 first entry. And to get y - 5, we want 0, 1, -5, correct? Because 0x + 1, 5, minus 5 will give us 1 - 5. And then to keep the 1, we just enter 0, 0, 1. And that will give us 1 in the third position with no x or y involved. So that's our matrix for the translation. Now for the rotation doesn't really require use of homogeneous coordinates, but we're going to introduce, we've started using them, we have to continue using them. Remember, in R2, the matrix for the rotation would look like cosine theta, sine theta, minus sine theta, cosine theta. So in homogeneous coordinates, it's in the upper left-hand side of the matrix. We'll have cosine 135 degrees minus sine 135 degrees, sine 135 degrees, cosine 135. So that's the rotation in R2. And then in the lower right corner, we have our 1, kind of represents the fact we're on the z = 1 plane. And then we fill in zeros elsewhere. And so we've incorporated that rotation in the xy plane into a 3 by 3 matrix that can be applied to our 3 Now I'm going to multiply these together to obtain the composition. We work from right to left here. The translation gets performed first. 1, 0, 3, 0, 1, negative 5, 0, 0, 1, followed by the rotation. And I'm going to go ahead and fill in values for these. I'm going to have negative square root of 2 over 2 is cosine of 135, minus square root of 2 over 2, 0. Sine of 135 is positive square root of 2 over 2. Then I have minus square root of 2 over 2, 0, 0, 0, 1. And all I got to do is multiply these two now to get a single matrix that will describe the composition of these two. And it's just standard matrix multiplication. So I'm going to have negative square root of 2 over 2. And I'm going to have negative square root of 2 over 2. And in the third position across, I'll have square root of 2 when I carry out the calculation. Then square root of 2 over 2, negative square root of 2 over 2, and 4 square root of 2 when I multiply the second row times third column, and I'll have 0, 0, 1 after I carry out the multiplication for the third row. So I kind of just wrote down the result. You can check, maybe I'll just verify one of these just so you can see. Let's take the second row in the third column here. So in order to get the 4 square root of 2 entry, I need to take 3 times square root of 2 over 2 minus 5 times negative square root of 2 over 2 plus 1 times 0. And notice that this is 3 root 2 over 2 plus 5 root 2 over 2 plus 0. There's the 8 root 2 over 2, or the 4 square root of 2. That's my entry in that location. So here is the matrix in R3 that gives us our transformation.